recording the lecture 4 of the mathematical modeling subject because I couldn't attend yesterday's lecture. Okay, so today we're going to talk about a little bit about the second order ODEs, how we can convert them into first order ODEs and solve them. And then mainly in this lecture, we're going to talk about some growth models, including the exponential growth model, the logistic growth model, the doomsday versus extinction. I will not discuss that in this lecture, but we will talk about that during the lectorial or the Thursday lecture. Okay, so the second order differential equations, so they will involve the independent variable x and the dependent variable y and its first derivative and also the second derivative. So it will be a function of all of these four will be a second order differential equation. And we will be able to simplify a second order differential equation whenever the dependent variable y or the independent variable x is missing from this second order equation. And then we can reduce it by a simple substitution to a first order equation. I will tell how we are going to do that in a real quick, but I'm not going to put a lot of effort on this because we're going to learn about how to solve second order ODEs later on in this course. Okay, so if the dependent variable y is missing, then our ODE will be a function of x and y prime and y double prime. In this case, we substitute p for the first derivative of y with respect to x. Then the second derivative of y with respect to x will be simply the first derivative of p with respect to x. Thus, if we use those to replace y prime and y double prime, we will get a first order equation with the variable x, p, and the first derivative of p. So this is the first order equation, and if we have constant coefficients, then this is something that we can solve using one of the methods that we discussed before, that is separating variables, or using the integrating factor method, or using a substitution. Okay, so we'll solve that, and let's say and then we found the solution p with the coefficient c1, and then to get y, because y prime is p, to get y we need to integrate the p function, whatever we got there, so we will get a second constant c2. Okay, so here's an example for that. I'll go through it really quickly, or I will just show you the first few steps of doing it. Let's look at it. We have x, dy on dx, and d2y on dx squared. So y is missing in this case. Therefore, let's substitute p for the first derivative of y. Then we know that the first derivative of p with respect to x will be the second derivative of y with respect to x. So if we replace the second derivative of, if we replace the terms and colon, if we use these two and plug into 1, we will get x dp on dx plus 2p equals 6x. So this is a first order ODE, which we can solve by separating the variable, maybe, perhaps, or maybe the integrating factor. Okay, so this is a first order ODE. Now, if we divide by x, we will get 2 upon x times p equal 6x. So this is a linear first order ODE we can use the integrating factor method. Integrating factor. Okay, so our integrating factor rho of x will be e to the integral of the p function. P is whatever the coefficient in front of this little p, so 2 on x dx. If we integrate it, we will get e to the 2 ln of x, and which we can write down as e to the ln of x squared or x squared. Our integrating factor is x squared. Now, if we multiply this one, we call it 2 by the integrating factor, we'll get x squared times dp on dx plus 2 on xp equal x squared times 6x. In the left hand side, we can write down as the derivative with respect to x times our integrating factor, which is x squared times p, and then the right hand side we have 6x cubed, and then we can integrate both sides with respect to x. Then we get in the left hand side x squared p, on the right hand side we'll get x to the 4. 6 divided by 4 is 3 divided by 2 plus a constant. Am I right? 6x squared okay, plus the constant, we call it C1, and I will continue the rest right here. So we'll get P as 3 on 2 x squared plus C1 upon x. That is P, which is the derivative of y. So y will be integral of P dx, or integral of 3 upon 2x squared plus C1 on x dx, which you can finish it off. I'm not going to do that. Okay, so I'm going to move forward, and the second is when the independent variable x is missing. So if the x is missing, then our ODE will be in the form of a function of y and its first and second derivatives equals to 0. In this case as well, we substitute p for the first derivative of y with respect to x, and therefore the second derivative of y with respect to x will be dp on dx. But look, since x is missing, we're going to come up with an ODE in terms of y. So dp on dx, we need to write down in terms of dp on dy. But we know dp on dx using the chain rule is dp on dy times dy on dx. And dy on dx is p. So dp on dy times p. P times dp on dy. Now, if we do that, we will get a first order differential equation with the terms y, p, and p times dp on dy. Okay, so now this is again a first order ODE which we can solve using one of the methods that we have used before, and then solving that we will get p of y with a constant c1, and then integrating that we will be able to get x as a function of y. This is called in the implicit form of the solution, which you can rearrange the terms and get the solution in terms of y. Okay, so I have example here for that as well, but I'm going to skip this because there is an easy way of solving this type of ODEs, which we are going to talk later in the course. So this is, I consider, as a harder way, but I just explain it to you so that you know there is a method, something like that. But I'm going to skip this. Okay, so the main theme for today's lecture is about the population models. Okay, we have already talked about a little bit about the population models beforehand. Population models describes the change in the population size, P of t, over the time t. So today we're going to explore various population models that accounts for the birth, death, and in more general growth patterns. The one that we have discussed in last week lecture is the exponential growth model, which is in the form of dp on dt equal k times p, where k is a constant growth rate to be exact. And we see that if this k is positive, the population is growing exponentially, and it increases to infinity. And if k was less than 0, we saw that it decays and that population is going to extinct. Now, that's what we discussed before, and we're going to learn about that more today as well. In addition to that, we're going to talk about some general population models with some variable births and death rates. For the exponential growth rate, it was a constant growth rate. And we also going to learn a new model which is known as the logistic growth model. Okay, now let's look at how we can model the change of the population due to birth and death rates. Suppose there is a population and it is changing due to the births and deaths with no immigration or emigration. So that means the only variation of this population is due to birth and death. No one is coming into this population and no one is going out from this population. Okay, so let beta be the birth rate and delta should be delta of t. Delta of t be the death rate. Write it again. Delta of t be the death rate. Then the number of births and deaths in a small time interval delta t we can compute as an amount of births. So we know the birth rate is beta. If we multiply it by the population, we will get actual birth rate. And then if we multiply by a small time interval, we will get the actual number of births. In a similar way, we can get the number of deaths by multiplying the death rate with the population and the time interval we are interested. Now, the change in the population due to the small time lapse is the difference between the birth rate and the difference between births and the deaths. Now, the rate of change of the population is the change of the population, which is delta p divided by the delta t. So if we divide this by the delta t, we will get beta of t minus delta of t times the population p of t. Now, if we take this delta t to be really small, then we get the differential equation where the dp on dt is beta t minus delta t times the pt, or very simply the first derivative of p with respect to t is beta minus delta times p itself. So this is a first order differential equation which we can solve because we have learned all the techniques in our previous lectures. Okay, now let's go back and explore a little bit more about the exponential growth model that we have already discussed before. When there is a constant growth rate, that means our k, which is the beta minus delta, will be a constant number. Okay, so if that's the case, then the population growth model reduces to first order ODE given by dp on dt equal k times p with the initial population of p naught. We can find the solution to this equation by separating the variable. I'm not going to do that. We already did before. And so this is our solution. P equal P naught times e to the kt. And also we explore that if k positive, this is t and p of t. This is the initial population. If k positive, the population grow exponentially, and t again p of t. If this is the initial population, if k negative, we see that it's going to extend. This is for the k negative. Okay, let's do the simple example. It's very simple. Suppose that an alligator population numbers 100 initially. Okay, let's note down the informations. We know it is 100 initially, or p of at t equals 0. And that its death rate is 0. So death rate, no one is dying. Wow, such alligator population. Let the birth rate to be proportional to the population. So beta is 0.0005. Very, very small amount. But still it's growing per year. And they are in years. And thus increase as the population does. Write down the initial value problem for the alligator population and find out the population in 10 and 20 years. Okay, so we can write it down. dp on dt is beta minus delta times p, right? The delta is 0, and in here beta actually is in form of times p. So it will be simply 0.0005 p with p of 0 equal p naught. Let me say instead 100. Yeah, that's our initial value problem. No, I think I did a mistake. Okay, so I did a mistake. I deleted some of the wrong stuff and I'm going to start again. So beta is 0.005 times p. Okay, that's our beta minus delta is 0 times p, or 0.0005 p squared. So that's the ODE, dp on dt. And then our initial condition p of 0 is 100. So that's our ODE, initial value problem. Now we need to find the p, which we can do by separating the variables. So 1 on p squared dp equals 0.0005 dt. And then let's integrate. 1 on p will be p to the minus 1 divided by minus 1, which is 0.0005 t plus a constant. Okay, so now, which is, let me write down as minus 1 on p, and we know at t equals 0, p is 100. We can use that to get the c, so 100, sorry, minus 1 on 100 should equals to c, because I have applied t equals 0. Okay, so that gives us as minus 1 on p equal 0.0005 t minus 1 on 100. Okay. Now, if I multiply by t, and if I multiply by 2000, we will get 2000 on p equal t minus 20, or we'll get, if I multiply by p as well, then I'll have the p right here. So p will be 2000 divided by 20 minus t. So I did two things. I divide by t minus 20 and then multiply by minus 1. Okay, so this is our solution, p. Now we need to find out p at 10 and 20 years. So p of 10 will be 2000 divided by 20 minus 10, which is 2000 divided by 10, which is 200. In 10 years time, we can see that the initial amount, which was 100, was doubled to 200. And what can we say about p of 20? If I apply t of 20, then this will be infinitely many, or we can see that p of 20 approach to infinity, because we get a divide by 0 at t equal 20. In 20 years time, even though this is a really small population growth rate, in 20 years of time, the population is going to be infinitely many. This is absurd. We need some deaths in this population. Otherwise they will close the globe. Okay, now. So yeah, I have dealt with the same problem. So this is what we got, and I have plotted I have a picture of the slope field for this problem, and you can see that no matter where we start, we're going to exponentially grow. The solution curves are going to grow exponentially no matter what was the initial population is. Yeah, but one exception. So if p of 0 is 0, if initially there was 0, then actually the population will remain at 0, or p of t equals 0. So this is a singular solution. This is a singular solution to this ODE, or the population will remain 0 if started with 0. That's quite obvious. Okay, now we see that the population of alligator can be infinitely many after some years, which is absurd, which cannot happen. So whenever we talk about the bounded populations, in the real world scenarios, the population actually cannot grow like that. So this exponential growth model is not a very good model that is caught correctly model the real world scenario. So for example, in many real world populations like human, fruit flies, the birth rate decreases as the population increases. Okay, so that's what really happens in the world. Okay, now there's a simple, let's look at how we can get into this logistic equation when we consider in that thing that the birth rate decreases with the population increases. As a simple model, birth rate is linearly decreasing. So we can say a birth rate is, initially it was b naught, constant, minus and then it decreases. So they say decreasing with decreasing rate. Beta 1 is the decreasing rate. And suppose in this particular case, our death rate is constant. Look at my letter, Mama. Okay, anyway, constant. Substituting these two into our general model, dp on dt equal beta minus delta times p. Beta is beta naught minus beta 1 p, and delta is delta naught. If we do that, we can simplify it into this form where a is beta naught minus delta naught and b is beta 1. We can write it in the form of a times p minus b times p squared. So this we called as the logistic equation. And here are some alternative forms. This is a form that I'm going to stick into most of the time. You will see why. If I take m as a divided by b and k as b, we can write down dp on dt as k times p times m minus p. So we have, again, this k and m are constant values. Okay, so this we call as the logistic equation, which can be used to model the real-world population scenarios where the birth rate is linearly decreasing, assuming the death rate is quite constant. Okay, let's do this example. Okay, consider the logistic population model with parameter k thieves and m thieves. Explore the solution of the logistic equation with these parameters. Okay, let's do it. We have our ODE dp on dt is k, which is 0.0004 times p times 150 minus m. That is the ODE, and let's say our initial condition is P0. Okay. Now, what happened to the P? This is wrong. This is not M, it is P. Come on. Okay, so I deleted the wrong stuff. Now, yes, with P of 0 equal P0. Okay, cool. Now, this we can solve this by separating the variables. Okay, if we separate variables, we will get p times 150 minus p dp in the left hand side, 0.0004 times p in the right hand side, not p. Come on. Okay, delta t instead. Yeah. So we get this, and then we can integrate both of the sides individually. How to do this? How to integrate this? What is your guess? We need to use the partial fraction. Partial fraction. Okay. Perhaps I can do it here, the partial fraction thing. Or maybe no, I'll do it here. I'll do it here. So let's do the partial fraction. So 1 on p 150 minus p, which I can write down as a on p plus b on 150 minus p, and the right hand side I can write down as p times 150p. By taking a common denominator, then we will have a times 150 minus p plus b times p. And now if you look at the numerator and look at the coefficients for the constant terms in the numerator, p of 0, in the left hand side we'll have 1, in the right hand side we will have 150 times a. Yeah, that's it. So our a is 1 upon 150. And if we consider the term with p to the power 1, the left hand side we do not have any p term. The right hand side we will have minus a plus b, which says that a equals to b, or that means the value of b is also 100, 1 on 150. So if we do that, we get 1 on 150, and then integral 1 on p plus 1 on 150 minus p dp equals to 0.0004 t plus a constant c. And now, which we can write down for multiply by 150, the right hand side, 150 times 0.0004 t plus this constant will be here, we'll get natural log of p plus the natural log of 150 minus p. Now, using the properties of the natural log, we can write down this as the natural log of p. Hold on, I think I did a mistake somewhere. Okay, the mistake is I need to divide this by minus 1. So that means this should be minus instead. That's not clear. So I'll just say minus 1, which gives me minus here, which I can write down as natural log of p divided by 150 minus p. Okay. And then in the right hand side, if we multiply by 150, we will get 0.06 t, and we'll get a new constant which I write as d. Okay. So p divided by 150 minus p will be another constant, let's say beta times e to the 0.06 t. Because when we take the exponential, I did two steps together here. I took the exponential of both sides, and then to represent the constant part, I use b. Okay. So it takes a lot of steps to solve this one. So p will be 150 minus p times beta times e to the 0.06 t. Then I'll go to here, and then we can collect all the p terms to the left hand side, so then we'll get p1 plus beta e to the 0.06 t equals, then we'll only have the other terms, which is 150 e to the 0.06 t. Oh, and then we have beta as well. Okay, so then we can get the p, which is beta times 150 times e to the 0.06 t divided by 1 plus beta e to the 0.06 t. Okay. Now we need to find out the value of b using our initial conditions. So at t equals 0, p equal p naught. So p naught equal beta 150, e to the 0 is 1, so 1 plus beta. And then if you solve this one, we solve this for the beta, which I'm going to skip because I don't have space here. We will get beta as p naught divided by 150 minus p naught. Let me call this as 1, and let's apply this to the equation 1. Then we'll get p equal p naught upon 150 minus p naught times 150 e to the 0.06 0.060 divided by 1 plus P naught upon 150 minus P naught. That's beta e to the 0.060, and then if I again simplify by multiplying 100 minus P naught and then arrange terms, we will get, which again I'm going to skip one or two steps. We get 150 P naught e to the 0.060 divided by P naught plus 150 minus P naught e to the minus 0.060. Look, I have a minus sign here. When I simplify things, we have a minus sign somehow at the end. Okay. Okay, so that's it. Cool. We can move forward. Yes. Oh, I had a lot of space. Anyway. Okay, so if I rewrite what I get at the end, it is 150 P naught divided by P naught plus 150 minus P naught. Oh, I think in the previous slide I did a mistake. Okay, so here we don't have this exponential term. We don't have the exponential term, so we don't have this term here because I have divided by that term. Okay. Yes, so e to the negative 0.06 t. Okay, so this is our final answer. And now, here I have drawn some solution curves starting with different initial conditions. P naught equal 20, 60, 120, 150. So you can see that as the time progresses, no matter where I started, the population is going to come to a value of 150. So population is going to converge to the value of 106, 150. So P of t approach 150, which is actually the value of m as t approach to infinity. So that means we can see that the population is not going to grow. It's going to come to a constant value, and that is the m. Okay. So if I sum up what we have discussed so far, the solution to the logistic equation, which is given in dp on dt equal k times p times m minus p with initial condition p naught, is given in this form. That means you really don't need to perform the integral all the time. If you can identify the given ODE is in the logistic equation, which is this, then this is its solution. So you can just remember it, or you can just use it. Okay. So if we know K and M and P naught, we know the P of T. Okay, so we have seen that already. Let's discuss it a little bit more. Limiting population and the carrying capacity in the logistic population model. The carrying capacity M, so we now have a name for the M. It is called carrying capacity. So that is the maximum population size that the environment can support in the long term. For a population model by the logistic equation, the population approaches M as the time progresses. We see that this in our previous example, and if we draw the solution curve for the logistic equation, we can see that if we started an initial population which is larger than the carrying capacity, then the population decay and approach the carrying capacity no matter where it started. And if it started below the carrying capacity, then the population rises and converge to the value of m. Okay. That's what's written here. The logistic equation helps model situation like limited resources, like the fruit flies in a closed container, so they have limited resources. For example, M we call as the environment carrying capacity. Okay, now let's look at this really nice example. It's about the U.S. population growth in 19th century. So the U.S. population was 5.308 million in 1800, and there's a record of 76.212 million in the 1900. Now we're going to actually analyze how the population, how the logistic equation and the exponential population model will model the population in the 19th century using this data. Okay, now taking P node as 5.308, so now our population are in million at time t equals 0, so that's our baseline is at 1800. Obtain the equation for the population using exponential model and also using the logistic model. So we're going to compare how each model is going to predict the population over the 19th century. Okay. If we consider the exponential growth model, we know the solution is given in terms of P naught e to the RT. All we need to do is identify the P naught and R using the given data. Now, we know that the P naught is the initial population. So P naught is 5.308. That's straightforward. And the next thing we need to find out is the R. So we know that at the 1900, this was the population. So 1900 is after a time of 100 years. So at t equal 100, the P is this. So that's the second data point we have. So using that, we can use that and write down 76.212 is equal to P naught times e to the 100. I apply t equal 100 and P equal this. So now we can solve this to get R. Okay, so I'm not going to tell how to get this one. So what we did, we just divide these two numbers and look at the natural log and then divide by 100 to get. So this is something like 0.026643. Thus, if we have used the natural growth model or the exponential growth model, the population will be given by this model. Okay, so you can see that our constant is a positive number. Say what we can expect to grow the population, for the population to grow exponentially over the time. Okay, so we're still in the same example. Now we're going to use the logistic growth model. Now, the logistic growth model actually helping counter the world in 1840. So I forgot the name of the person who invented this one. Anyway, so he invented it in 1840. Okay, now we're going to use the logistic growth model. In the logistic growth model, we have like three unknowns: P naught, M, and K. So to identify them, we need three data points. Initially, we had 2 data points, and suppose we knew the population at 1850 as 23.192 million. we already found out that the p node is 5.308, and then so this equation we can obtain using the data at 1850, where the t is 50, and then this equation we can obtain using the data at 1900, where the t is 100, counting from 1800. So now with solving these two, one can obtain the value for the k and the m. So it now has like a limiting or carrying capacity of 188.121. Okay, so if we put all together, we get this logistic model for the US population. Now, which one you think better describe the population in United States? The logistic one or the exponential growth model? Okay. So, to discuss that, what we can actually do is one can look at the population data over the time in US and look at the error between the actual population and of each model. And in here I have a graph starting from 1800 and then going even until 1950. So you can see that the error percentage, as a percentage wise, the exponential growth model has a higher error. Look, it was like 20% error in the middle of the century, and then after 900 the error is negative. That means because in the exponential growth model like it predict like this, so the error is negative. So that means it over predicting. After the 1900, it's hugely over predicting the population. But if you look at the logistic model, the error is much smaller, even, and it gives a reasonably good approximation even at the 1950, because we use the data at 1800, 1850 and 1900. Okay. So logistic model is way better to predict the population growth in US. Okay, one more thing that we need to be really careful about: one should not expect too much of the model that are based on several limited data. So for the exponential growth model, we use only 2 data points. And for the logistic model, we use only 3 data points. They are really less number of data points. And then these models, we cannot expect much from them because they were based on limited data. So if you want to have a more accurate data that representing whatever we are modeling, we actually need more data that better describe the situation. Okay, so here I have few more slides, just 2 more slides. I'll go through them a little bit quickly. Applications of the logistic equation. The limited environment is one situation that we can apply. If a population is limited by a maximum capacity m and the growth rate is proportional to the minus p, then we will come up with our logistic model. For example, the fruit flies population in a closed container. The second application is if the birth rate is constant and death rate is proportional to p. Previously, remember, we had a constant death rate with a decreasing birth rate. That case also the logistic equation worked. That's how we define it. It also works when we have a constant birth rate with increasing death rate. For example, modeling of aggressive or cannibalistic species is an example for the competition type situation. The joint proportion is another one. The spread of disease of rumor is another thing that we can use the logistic equation. If P of T are infected and M is the total population, again we will come up with the logistic equation. So for example, models rumors spread in a fixed size group. We have one example for that. I'll try to do it really quickly, and that will be our last slide. Okay, let's look at this. Example 41. Suppose that at time 0 there was 10,000 people in a city with a population of 100,000. So that's our carrying capacity. Our carrying capacity is 100,000. Have heard a rumor. So out of this 100,000, 10,000 people heard a rumor. After 1 week, the number of people who have heard the rumor increases to 20,000. After 1 week, it becomes doubled. Assuming the population spread follows a logistic model, we want to determine when 80% of the population will have heard the rumor. Okay, so we're going to start with the logistic population model. M P naught P naught plus M minus P naught e to the minus KMT. So that's how we use that. That's the population. That's the solution for the logistic growth model. And then we have with M equal 100, that is our carrying capacity, and P naught is 10. Okay, the only thing that unknown to us is the K. To get K, we can use this data point, P of 1 equal 20,000. Okay. So look, so everything is in thousands. Okay. P is in thousands. So P of 1 equal to 20 when we consider it in thousands. So 20, if I apply that to the solution, 200, sorry, not 200, 100, that's M times P naught, which is 10 divided by 10 plus M minus P naught is 90, e to the minus M is 100, K, T is 1. Okay. If we plot that, and then if we solve this one, you will get a value of K as 0.00819. So now we know all the parameters we need, and what we need to find out is P, the time that P become 80. Let's say at T equal T1, let's say P of T1 is 80. And then if we apply this to our logistic model, 80 should be M is 100, P naught is 10 divided by 10 plus 90 e to the minus 100 times K, which will be 0.819 T1. Okay. All we need to do is solve this and get the value of T1. You will get the value of T1 as 4.419 weeks. That means 4 weeks and 3 days. Look. Ooh. Within 4 weeks and 3 days time, 80% of the population know about this room. Okay, I'll stop there.